My name is Yuriy Bezsonov, and I am Senior Solution Architect at AWS. In my role, I work with the customers and AWS partners on solutions related to container technologies. In today's talk, I am going to walk you through a journey which we see customers are facing when choosing to build their own internal development platform or internal delivery platform and expose internal APIs on top of Kubernetes. We will discuss today the different application delivery streams we see out of there, what are infrastructure's controllers and how you can use them to accelerate delivery time of your application. We also define what are compositions in Kubernetes and review the tooling that support it. We are going to finish with an overview of a solution that you can try in your own environment. But before we talk about delivery streams, let's define a problem statement. Let's set up the context with a sample application. Our sample application is taken from EKS workshop, and it is a good representation of an application that consists of multiple sub-applications which have one or more components. Those components can be runtime components, for example, Kubernetes pod deployment, services, ingresses, which live inside the cluster, inside the Kubernetes cluster, and also infrastructure resources, such as AWS services in this case, which lives outside of the cluster, for example, Amazon DynamoDB, Amazon MQ, or Amazon Relational Database services. When deploying an application, we need to consider not only deploying its runtime, but also its backend services. And in this case, we need to take care about the components which live inside the cluster and outside of Kubernetes cluster. In the next slides, I will walk you through some of the delivery streams we see out of there, some of the delivery methods, and the time it takes to deploy an application in each stream. The first stream is when developers simply deploy their runtimes and configuration to Kubernetes. Usually, the components Kubernetes configuration and its runtime group together in a single repository. Kubernetes supports the creation of and management of external networking and storage services since the very beginning, and those AWS response resources which corresponds to those services can be managed in a single stream as part of application runtime configuration. For example, Kubernetes manifests such as services, ingress, and persistent volumes can in turn deploy application load balancer, network load balancer, and persistent load balancer using the Kubernetes constructs. These delivery streams usually takes minutes to complete. The second stream, more complicated stream, usually happens when additional backend services are needed. A pattern which we see is an infrastructure definition repository that holds the entire organizational infrastructure as a code definition, for example, Amazon DynamoDB, RDS, S3, and other components. An infrastructure, DevOps, or platform team, you may have different names for those teams, needs to approve the pull request, which will trigger the creation of AWS services in AWS account. Since this stream includes handover process from one team to another, these delivery streams can take sometimes. The last stream is the slowest one. It involves some traditional ticketing system to provision resources. The database team here is just an example. It can be any other team. But the pattern here is that the developers have no way to influence or trigger a change on the infrastructure service side, and they have to wait for other team to proceed their request to fulfill their tickets. And the question that we ask ourselves, and developers often ask ourselves, how we can make the deployment process faster, how we can improve turnaround from changing the line of code of the application to deployed infrastructure and running application in the cloud. And before diving into techniques and practices of achieving this, of improving this process, let's set the requirement of each team, because they are different. From a platform team perspective, they want to build consistent deployment process while enforcing organizational standards. They need secure environment, they need compliant environment, and they need observability because they may have many environments from various teams. Application developers, on the other hand, want to have full ownership of their application components, including its backend infrastructure services, and they would like to have it in the easy way, and they would like to have it fast. In the infrastructure as a code domain, we already saw a definition of clear boundaries and ownership when provisioning resources. This quote is taken from AWS Cloud Deployment Kit CDK Best Practices Guide, and it calls out that whoever that develop and manage the runtime should also manage the infrastructure. That's why infrastructure and runtime code should live in the same package, in the same repository. When you scan this QR code, it will take you to AWS CDK Best Practices Guide, where you can read the details of that approach. And by applying this practice, we can see now that a developer managed both the runtime and the infrastructure definition in the same code repository. Once code is being merged, two streams are triggered automatically. One to Kubernetes, to the cluster, creating the runtime, deployment pod, and so on. And the existing backend services we discussed previously, like load balancer or persistent volume, which can be deployed from the cluster. The second stream goes directly to an infrastructure as a code tooling, whether it's AWS CDK, which generate a CloudFormation template, or Terraform. And in turn, these tools creates the needed infrastructure. Applying this practice reduces the deployment time from hours to minutes. Focusing on Kubernetes again, we can build a similar process using the well-known operators framework to build and maintain external services from within Kubernetes. It's true that operators frameworks can be used to deploy and maintain external system to Kubernetes, but writing your own operator, it is rather complex and what I would call undifferentiated heavy lifting. This is where pre-built infrastructure controllers can help us significantly speed up implementation time. Those infrastructure controllers are pre-built controllers that allow you to manage cloud services using your known Kubernetes API, like you do it with your runtime. It allows you to create your own platform API on top of Kubernetes and have a declarative infrastructure configuration, which would help you leverage the Kubernetes ecosystem to provision external resources as well as internal resources in the cluster. Two of the main tools available now are AWS Controller for Kubernetes, in short ACK, and Crossplane. ACK is developed by AWS. It enables the management of a variety of AWS resources, AWS services, and it is supported by AWS. Crossplane is a CNCF open source project with an extensible framework and has a broad community around it. Returning to our previous diagram, we can see how those tooling can help us to provision the application backend services. At that point, developer might ask if that means that they need to have extensible knowledge around infrastructure configuration and need to know how to deploy those various cloud services, how to combine them together in the right way. And no, it's not necessary. Let's have a look at this example. On the bottom, developers simply request database instances. It doesn't really matter which instances the developers need database. Of course, after that they have a responsibility to configure it upon creation, ensure it is running, and being able to modify it when necessary, to have control over that database instance. However, the platform team might decide to have different implementation depends on when this instance runs, in cloud or on-premise, and abstract the implementation details from the developer. In our example, we see that the platform team can decide to implement this database instance on-premise using a PostgreSQL database and Prometheus instance for observability. On the other hand, on AWS, they want to leverage IAM for authentication, Amazon RDS for database, and Amazon CloudWatch for observability, and use more managed services to reduce operational overhead. This method is usually called a composition, which means an abstraction of the underlying implementation details by providing simple set of API. Going back to infrastructure as a code, we already have this capability of building abstraction of different implementations, while providing clear interfaces on how to consume this. And as you can see in this slide, these quotes can be taken from the documentation side of AWS CDK and HashiCorp Terraform, and describe exactly that. Composition is the key pattern for defining high-level abstractions through construct. In AWS CDK, we even call it the same way, a composition. Going back to the previous diagram, this is now how we would use infrastructure as a code tooling with composition to abstract the implementation detail of our database instance. But how does composition looks in Kubernetes? The CNCF Application Delivery Workgroup published the platform whitepaper, calling out 2 open source projects available now that can help with compositions. Those projects are Kubevela and Crossplane. Kubevela is software delivery platform that implements an open application model. This model focuses on building applications rather than configuring Kubernetes objects and can be more natural, more native for developers. Crossplane is the same tool that we discussed previously, but this time it is about the capability to build platform on top of Kubernetes, as well as providing infrastructure controllers. Another advantage of using Kubernetes API to provision AWS resources is that you can leverage the extensive ecosystem tooling to package, deploy, and validate your infrastructure definitions. It's the same way like you would use it with runtime configuration with your manifest, deployment, and pods. A small example can be using Helm or CDK8s for packaging components, Argo CD or Flux for GitOps to reconcile the state of repository with the state of the cluster and infrastructure, Kyverno or Open Policy Agent for policy enforcement, and variety of other tooling from the Kubernetes ecosystem. To demonstrate how to use it in practice, how to use composition and infrastructure controllers together, we at AWS built a solution reference for managing AWS services using infrastructure controllers through compositions. In this solution, we demonstrate how to provision Amazon EKS cluster using compositions and infrastructure controllers. Yes, you can even provision the cluster itself with the help of compositions. Once a platform team adds a cluster composition manifest to the repository, the GitOps tooling reconciles the composition request, and which in turn triggers the creation of a cluster with all the needed tooling deployed to that cluster. You have that cluster with all the necessary components which allow you to do next step. The solution also describes an application onboarding process where a developer commits its runtime code and infrastructure configuration to the application-specific Git repository. After that, the developer creates a pull request to centralize the repository, so the cluster GitOps tooling will start reconcile the application-specific repository. Once the platform team approves the PR, the GitOps tooling starts the reconciliation of application repository. From there, the cluster infrastructure controller tooling will provision the relevant AWS resources for that specific application. It will create a complete life cycle from the written line of code to deployed application with all of the required infrastructure and solution components. The solution itself is covered in the series of blog posts and have a detailed sample code to get started with. If you scan this QR code, you will get additional information and you will be able to try this solution in your own AWS account. To summarize what we learned today, we saw how grouping runtime and infrastructure defines clear responsibility boundaries, how infrastructure controllers extend Kubernetes capabilities to provision AWS services. We also seen that Kubernetes API can enable standardization. This allowed us to leverage the Kubernetes ecosystem tooling, especially GitOps, for provisioning not only Kubernetes resources, but also infrastructure resources. With that, I would like to say thank you. I hope you enjoyed the session, and please feel free to reach out on LinkedIn and have a discussion about anything related platform, containers, and architectures. And I would really appreciate if you spend 1 minute and answer on a short survey about the sessions. Your feedback is very valuable. Thank you.